Hi, um, I'm Dr. Vicky. We're going to talk about growth curve determination of fish. And before you talk about this growth curve determination, it comes in due to stock assessments. What are the stock assessments? Stock assessments are the scientific processes that are used to determine the size, the nature, the structure, the health, and the sustainability of fish population. It can be in a managed condition or in a controlled condition. In order to know the trends, to determine the trends of that fish population within a particular period of time. It also helps for management of fisheries and fisheries byproducts. Now, this growth curve determination, this growth curve that has to do with the relationship between the length and the age of these fishes. And for you to calculate growth curve determination, you use Von Bertalanffy's model. Yes. This model states that fishes at their early stage or young age grows faster. Then at a level where they reach their maximum size, they tend to have a slow growth. And what enables fishes to grow faster is good environmental condition. Just like we humans, if you have a better environment, the tendency of growth becomes 100% or 95%. Then another factor that enables fast or rapid growth at any stage, mostly according to Von Bertalanffy's model, is good feeding habits or availability of feed or food. What makes fishes not to do well mostly or to slow down here is maybe pressure, lack of feed availability, and poor environmental factor. Stress too can also be a factor that can lead to a less growth at their maximum size. Assuming we have we are going to have growth curve determination. I told you it has to do with the determining the relationship that exists between the length and ages of fish within a sample data. And in this length and age, you still talk about the maximum length and the asymptotic length. And this for you to calculate this model, we have to use the Von Bertalanffy's model. Why do we use the Von Bertalanffy model? Because it is realistic and it helps to show the length. It helps to predict the length of fishes at several ages within the given set data. Then it also helps for you to know the length that exists within the sample population. It is realistic in nature. Now, in this growth curve determination, let's assume we have a sample set data of ages and lengths. Let's say the age, which is the T, you have 1, 2, 3, 4, 5. Then you have length. The length can be the mean length. Okay, the length is in centimeter. You have the first length, you have 8.3, you have 14.1, you have 18.0. Then you also have you have 20.5, and you have 22.0 centimeter. These are all in centimeter. Why this? They are the years of existence of that particular fish or sample data. Now, for you to calculate this, what you need to do is to use, okay, for instance, when you have this ages and length, and you're asked to estimate, you estimate the L asymptotic. The second one, you're asked to look for the linear relationship between the growth of the equation. Then the next one, you have to estimate the growth coefficient. That's the K. There you use slope to do it. Then the next one, you can be asked to predict the mean length of fishes at age 3 and 5. Then you can also be asked to state or make comments on the fish status based on the sample data that was given in the equation. So these are the possible questions that you can get. And for you to solve this, we are going to look at the Von Bertalanffy's theory equation. The Von Bertalanffy. First of all, if this is the Von Bertalanffy's equation, where you have the LT equals to L asymptotic, bracket open 1 minus E raised to power K, bracket open T. The LT is known as the predicted length at age of the fish sample. Okay, then the L asymptotic, this is known as the asymptotic length or growth. Let's say asymptotic growth, or you call it the maximum growth or length of the fish sample. Then the E, and don't forget we have the K too. The E is known as the exponential coefficient. And this exponential coefficient is constant, 2.718. That's the value for it. Then this K here, this K you're seeing, this K has to do with the growth coefficient. Then the T you're seeing here is known as the theoretical age. Okay, when T is equals to 0. Sometimes you can see it in some formulas, TO equals to 0. Sometimes this TO is assumed. Sometimes the TO is also given in an equation. In a data set, you can get TO. You can be given TO. Then this asymptotic growth or maximum growth, sometimes it is being given in a question set, in a question within a data set. Then sometimes it's not given. So I will give you an example of a question in which you have a data set without the asymptotic length. Then I will show you how to look for the asymptotic length. Now, this is it. Now, in the question, you've been given this age, and length within a data set of a given population. These are basically population of smaller fishes, probably the tilapia nilotica. Okay, then now we are asked to look to estimate the length asymptotic. Okay, for you to look for the length asymptotic, now in our given sets or the set of data, the maximum, you look for the maximum length, because this symbol is known as asymptotic, which can be the maximum length, and you're given a set of data. You have 8.3, 14.1, 18.0, 20.5, and 22.0, all in centimeter, because it is the length. Then now you look for the larger length, which is 22.0. So this is the data set, and these are ages and the length of fish. For you to calculate the length asymptotic, you need to look for the highest number or size of the fish within this population. If you check, we have 8.3, 14.1 cm, 18.0 cm, 20.5 cm, and 22.0 cm. This is the largest size of the fish within this population. Now it is 22.0 cm. Now fishes rarely reach their maximum size potentials in a particular population. So fishery scientists came up with an empirical conditional factor which states that within a population of fish sample, about 95% of fishes usually reach their asymptotic length or their maximum length. So if the scientific or empirical conditional factor could state that fishes rarely reach about 95% of their maximum or asymptotic length. If you look at 95%, for you to look at 95%, if fishes rarely reach 95% of their asymptotic length within a given population or within a sample now of catch, this is 95%. For you to get 95%, what you do is that 95 divided by 100, you have 0.95. This is what it means. This is gotten from empirical studies of fisheries research. Fishes, it has been observed that fishes rarely reach 95% of fishes rarely reach their asymptotic lengths within a fish population. So now, see, if they rarely reach 95%, 95 divided by 100 will give 0.09. Now, in our own data sets, the highest is 22.0. So what you do is that you bring down this asymptotic length, which is equals to 22.0 cm, divide by, you can leave the cm, 22.0 divide by 0.95. Fishes, since it has been observed that 95% of fishes observed rarely reach their asymptotic length or maximum length in a given population. So 95 divided by 100 will give you 0.95. So now in our data set, the highest value is 22.0. So you bring this 22.0 divide by 0.95, which will give you what? 23.1. Let me check. 23.15, approximately 22. Okay, to give you 22. Now our asymptotic length does not stop here. Asymptotic length is supposed to be, you have to add 2 to 3 points of this your length measurement that you have. Okay, that is the pattern when you're using von Bertalanffy's equation. So you have 22.3. You can round it up. If you add 2 points, you have 20. This is 23, 24, and 25. So this is you can use 2 to 3 points. So 25 in this case, that's what we are using. So after getting your asymptotic length, after you divide the 95% of fishes observed within their population, you now add 2 to 3 points. You can use 2 to 3 points for you to get the final asymptotic length. So in this case, we are using 25. You can also use 26. It depends, but you don't forget you can use 2 to 3 points. This is the first point, this is the second point, and this is the third point. Even if you have 23.5, you naturally, you know that, for instance, this our length now is 23.5. Maybe from the length that is being observed within the sample, you can either say 23, you can approximate to be 24. So when you want to start, you say 24, 1, 22, 25, 2, then 26. So you can use either 25 or use 26. That is just how to calculate or to determine your length asymptotic if it is not given to you from the questions. Like in this our case, the asymptotic length was not given. We were asked to look for the asymptotic length. So I can clean here now. To estimate the growth coefficients. Okay, linearize the growth equation. Okay, now this is the data set, and we've calculated our asymptotic length, which is the first one. Our asymptotic length as L asymptotic, which is equals to what? 20, which is equals to 25. Okay, this is our asymptotic length, 25. Okay, so the asymptotic length we've gotten the asymptotic length as 25. Now the next question we have to look is to linearize the growth of the equation. That's the second question. Linearize the growth of the equation. For you to linearize the growth of the equation, what you have to do is that from the formula of Von Bertalanffy 2, we are going to linearize the equation. Now for you to linearize the equation now, what you will do is that from the formula of Von Bertalanffy 1, LT all over L, okay, equals to minus K T. Then the second one, and in 1 minus LT all over L asymptotic equals to minus K bracket T. Okay, this K is raised to power T. Okay, this is how it is. For you to linearize this is the linearized form of Von Bertalanffy's equation. So what you will do is that since we've been given since L asymptotic is equals to 25, you're going to substitute your L asymptotic into where you have this 25 into where you have the L asymptotic. So now you have your age which is T, then you have your length, which is the mean length. This mean length is in cm. Okay, now you have the first formula for the linear Von Bertalanffy's theory. Then you have the second one. You have the second one in of 1 minus LT all over L asymptotic. Now, this your mean length. It can also be called the this mean is in cm. It can also be called the LT. Okay, good. In the ages, we have 1, we have 2, we have 3, we have 4, we have 5. Good. Now the mean length is 8.3. The next one is 14.1. The next one 18.0. The next one 20.5. The next one 22.0. Good. For you to get this, what you have to do is that, okay, so this is what you do for you to calculate the linear form of the equation. What you do is that from Von Bertalanffy's theory, you have one, the length all over asymptotic length. That's the constant k. We've not gotten the constant k anyway. Then, and this the in 1 minus asymptotic length all over. So this is how it is. We now know our asymptotic length as 25. What we'll do here is that the age, the mean length, the first linear equation, the second linear equation. Now, what you do is that LT, which is the length, is 8.3. Divide by 25. You get the value. Then now you minus 1. You minus 1 from the value which you have, which will be 0.668. You repeat the same thing for this other place. 14 divided by 25. Then any value you get, 1 minus that value, it will give you 0.436. Then the next one is 18 divided by 25. It will give you a particular value. Then that value you get, 1 minus the value you get, it will give you 0.286. The next one will 280. The next one 20.5 divided by the 25 to give you a figure. Then when you minus it from the figure, you get 0.180. 22 is the next length. 22 divided by 25. Then when you get your value, 1 minus that value, it will give you 0.120. This is how it is. Then now what you do is that the in factor of this value, the in of 0.668, what will it give you? To give you minus 0.40. The in value of 0.436 will give you minus 0.83. Okay, minus 0.83. The in value of 0.280, it will give you minus 0.43, 0.43683. Okay, let's just assume the in value of 0.80 will give you minus 1.27. Good. The in value of 0.180 will give you minus 1.71. The in value of 0.120 will give you minus 2.13. Good. This is just what you have to do. So the next thing you do is that you have to plot a graph. You have to plot a graph, and this graph now you will use the in factor and the t, which is the age. Now this in factor will be in the y-axis, the age will be in the x and the x-axis. This is the graph. LT all over L asymptotic against the age, which is the t. Okay, so So you have to plot the graph against this. So this now will be zero. This is your x-axis. Age, or you can call it the year, or you can call it t. Okay, then this is one, age 1, age 2, age 3, age 4, age 5. Now this is your y-axis, and now each square in this x-axis contains 1 year, whereas in this y-axis, you have this minus. So what you do is that, you know, you have 1, 2, 3, 4, 5 units. So each of these units will contain 0.5 minus 0.5. So each has 0.1, 0.2, 0.3, 0.4, 0.5. Then the next 1, 2, 3, 4, 5 is 1.0 minus 1.0. 1, 2, 3, 4, 5 minus 1.5. 1, 2, 3, 4, 5 minus 2.0. 1, 2, 3, 4, 5 minus 2.5. Look at the in factor. You see that you have 2.13, right? That's 2.1. So basically you can still continue. It depends on the length you have. Minus 3.0. Good. So now on this axis, now the x-axis, age 1 is giving us, look here, this is age 1, this is the first one, minus 0.40, which is minus 0.4. You come here, this is 0.1 minus 0.1, 0.2, 0.3, 0.4. So you strike it here, and don't forget your answer must be in a linear form. That's why they say linearize the equation. Then in 2 you have 0.83, which is 0.8. This is 5, 6, 7, 8, somewhere here. Somewhere here. Then in age 3 you have minus 1.27. So you trace it, age 3, 1.27. This is okay, 1.27. This is 1.1 minus 1.2 minus, so invariably you can approximate to be 1.3. Okay, so this is 1.1, 1.2, 1.3, somewhere here. I need to get this line. This is age 3, somewhere here. Okay, then now age 4, 1.7, 1 minus 1.7. This is 1.6, 1.7, somewhere here at age 4. Then age 5 is giving you minus 2.13, which is minus 2.1. Then you come over here, this is 2.1 under age 5. Your graph must be in a linear form. So if you check, this is the maximum length. We have to clean all this. I just did this to get the tracing to make sure it is in a linear form. This is the maximum, and this is the lower length. This is the lower length. Okay, so that is that for this, for you to be able to get your linear length, or the length in a linear form. So we are not done. We are going to calculate the K, this k factor. So now we are going to check the k, which is the slope. Okay, for you to check the slope, okay, you have change in y all over change in what? X. This one now is the y all over the x. Okay, now you're going to use the coordinate of 2 points. The coordinate of 2 points, if you check your a, your point a, point a is what? The first point here is 1, and what? The point a is 1 and minus 0.4. Look at it very well. That's your point a. Your point a is 4 and minus 0.4. Then your point b is 5 and minus 2.1. Okay, this is how it is. Hold on first. Now we are going to read the coordinates from the graph below. I told you that in slope we've already checked the linear equation of this, so we are estimating the slope now, which is the coefficients. Okay, from the equation, estimate the coefficient of factor of from the equation, which is slope k. You can use it. So changing y all over changing x. This is the point. Point a is 1, h1. Then point b, point h1 to 0. Minus 0.4. Point b. So you can actually read is b is 5 to 2.1, which is this 5 at minus 2.1. So you can read the coordinates. Read the coordinates from the points. Okay, from the length, from the points in the graph or the length in the graph. So read the coordinates from the graph. Okay, so if you're to use the graph now to read the coordinates, you know that your x1 is equals to this first one, which is 1. Your x2 is equals to 5. Then your y1 is equals to minus 0.4. Your y2 is equals to minus 2.1. That's it. Okay, so now from your slope formula, slope, which is minus k, anyhow you want to put it, then is changing x, which you've already done. You're changing y minus changing x, which is y2 minus y1 all over x2 minus x1, which is equals to your y1 here is y2 is minus 2.1 brackets, okay, minus, this minus has to be here, brackets, your y1 is minus 0.4. Then your x2 is 5 minus x1 1. So if you're to do this, you will have 0. You know, even if you're doing it minus 2.1 plus 0.4, minus times minus is plus all over 4. 5 minus 1, which will give you minus 1.72 all over 4. It will now give you what? Minus 0.43. Okay, minus 0.43. So now you know that from your Von Bertalanffy's equation, your k is minus k, right? The k is minus k. So for you to remove the minus, you can as well do minus equals to 0.43. So you have the predicted length of 3 and 5. Okay, so you know that from your equation, LT is equals to L asymptotic bracket 1 minus E raised to the power KT. Okay, can still close it. So your L predicted, this L asymptotic is equals to 25 cm. Then your E is equals to 2.718. Your K is equals to 0.43 from that slope we calculated. Then your T is equals to the theoretical length that is being given, 3. Okay, so what you do is that you bring the formula is equals to 25 bracket 1 minus E minus 0.43, which is the K, bracket T, which is 3. Okay, then this is equals to 25. Let's open this. 1 minus, this is what, E, 0.43 times 3. 0.43 times 3, let me calculate. 0.43 times 3 will give you minus 1.29. Good. So you all know that your LT is equals to 25 brackets 1 minus 2.718, which is the coefficient of this E raised to power minus 1.29. So let's do this. Let's simplify this first. Cut. Let's see. So 1 minus 0.725, you have 0.725, 8.25, or 18.125, or 18.1. You cannot approximate now, so it's still 18.1. So that is to say that the predicted length of 3 and 5 is 18.1. If you look at our data set, you see that is within the length. Is within the length that was given from the data set. The range is within the length that was given from the data set. Even if it will be far, it shouldn't be much. Then for predicted length, of 5. For predicted length of 5. Okay, so from the formula, L equals to L asymptotic, brackets 1 minus E minus K T. So your LT, we all know what is the L asymptotic, which is 25 bracket 1 minus 2.718 raised to power minus 0.43 bracket 5. So we just had to put all the values. So your LT, predicted length 25 bracket 1 minus 2.718 raised to power minus 0.43 times 5 will give you minus 2.15. Okay, so what you have to do is to 1 minus this minus 2.178 raised to power 2.15. Let's see what the value is. 2.7 LT equals to 25 raised open bracket 1 minus 0 0 LT is equals to times 25. 25 times this will give you 22.1. So that's the centimeter. Okay, adjust it. So that's to show that within the given data and the predicted length, from the data you see that the length is invariably the same thing, or within the same range. So when you calculate and it's within the same range, you know that what you're doing is actually correct, and it shouldn't exceed a particular point or length. It should just be within that. It shouldn't be far or more than the length of the given data. That's just it. It's on the age and length of to predict the future trend of the sample within this data. You see that if the asymptotic length is 25 centimeter, so if you're asked to calculate the asymptotic length, or predict the future trend, just know that at younger age the fishes tends to have a rapid growth. Then as they grow to their maximum length, age and length of the fish status from the calculation, okay, what you suggest about the fish stock within that data population. You know that the calculation of the length and age relationship shows that fish length increases rapidly at younger ages and slow down at age. When it increases, it slows down. Now when they approach the asymptotic length of 25, they tend to slow down. The predicted length of the fishes within this region of 3 and 5, you notice that it is within the predicted length of 3 and 5. If you observe, they are very close to that of the observed value within the data sample, which is 18.0 thereabout and 22.5 thereabout, because we are looking at age 3 and age 5. Okay, this indicates a good fit of the Von Bertalanffy's model. Then when you check about the K constant, which is the K slope, the K slope we had is minus 0.43. okay, it suggests that the fish species exhibit moderate growth, reaching near maximum size within few years, since most of the fishes attain a large population of their maximum length at age 5. If you check at age 5, you see that it is 22.1. Most of the fishes within these ages, within this data set, obtain their maximum length at what? Age 5. Okay, now the stock appear to be dominant of matured fishes. If you check the stock here, they appear to be dominant of matured fishes at this age 5. Then this pattern suggests that the fish stock is not severely overfished. And the individual have sufficient time to grow more before reaching their asymptotic length. You know that the asymptotic length is 25, and if at age 5, which is the higher length in this our given data or data set, is 22.1, that is to say that before they could reach their asymptotic length, is to say that before the fishes could reach at age 5, if they could reach 22.1 centimeter, which is at age 5 years, and in the asymptotic length that we use was 25 centimeter, that means if they could reach this 22 centimeter at age 5 here, that means the individuals, they have sufficient time to grow before reaching the asymptotic length of 25. That means they can live grow exceeding this value of 22.1 centimeter at age 5. They can grow above that. That is just it.